Assalamu alaikum wa rahmatullahi wa barakatuh, and good morning everyone. My name is Yusuf Hussein Abdussalam. I am PhD student at University Malaysia Bahang. Today I will present my paper about assessment of heavy metal contamination of agriculture and mining soil around Chini Lake. Implication of the seasonal variation. Introduction. Chini is a land marsh with the unique biodiversity of plants and animals. Several rivers, lakes, wetlands, and inland forests are all part of the watershed. Since May 2008, UNESCO has designated the Chini watershed as biosphere reserve due it is the abundance of the natural resource. Regardless of the classification, the surrounding Chini has been developed for agriculture, settlement, and tourism. Heavy metals are normally occurring element and environmental, but there were disparate uses for the human use, such as agriculture, industry, mining, coal boring, power plants, and metallurgy has alterated their atmospheric geochemical cycle. This picture showing the current issue of the Chini: land clearing, mining activity, land for development, sedimentation, eutrophication. Materials and method. Water sampling. This study was investigated the population impact of the anthropogenic impact over the soil sediment in the Chini. 10 selected heavy metals were measured from 10 sampling stations in the lake during wet and dry season. 4 stations in the agriculture area and 3 stations in the forest area and 3 stations in the mining area, as we see in the figure number 1. Approximately 500 grams soil, depth between 0 to 15 centimeters, were sampled using the auger with the tree replication. Soil samples were dried at room temperature and roots, small stones and leaves were separated from the soil. Samples were then saved and soil lumps were crushed. The variation in mean value of the physiochemical parameters among the three types were determined using one-way analysis of variance SPSS, sample, producer, and preparation. 3 replications of the sediment were collected with the aid of the electronic vibration core sampler tube, which enables sampling efficiently to depth of 8 meters. Following the packing of sediment sample in a polythene bag and chilled in ice boxes, they were transported to the laboratory for the further analysis. The samples were dried overnight at 155 cellulose to constant weight for the heavy metal analysis. Result and discussion. Heavy metal contamination of soil. Number 1, arsenic. The arsenic concentration were varied from 0.17 to 2.24 ppb, and the average of 0.69 plus minus 0.58 ppb. The highest arsenic concentration was 2.24 was recorded at the Station 7 forest area during the dry and wet season, followed by the Station 8 in the mining area. Negative correlation was found between the arsenic and pH, AC, and sand. Number 2, copper, Cu. The copper concentration ranged between 0.14 to 1.83 ppb, an average of 0.92 plus minus 0.46 ppb. Maximum Cu concentration was recorded at the station mining area 8, which is 1.83 ppb during the dry season, whereas the last polluted station was found at the station 10 mining area during the wet season. Personal correlation shows the significant negative correlation among the Cu and pH, AC, and sand, whereas the significant positive correlation with all selected heavy metals. Number 3, cobalt. The cobalt concentration ranged between 0.76 to 6.40 ppb, and the average of 2.74 plus minus 1.89 ppb. Maximum CO concentration was recorded at the Station 1 agriculture area 6.40 ppb during the dry season, whereas the last pollution found at the Station 6 0.76 ppb for CO during the wet season. CO had significant negative correlation with pH, AC, and sand, whereas that had significant positive correlation with the salt and another 9 selected heavy metals. Manganese concentration recording between 0.43 to 99.22 ppb, and an average of the 11.51 plus minus to 1.08 ppb. Maximum manganese concentration recording at the Station 1 agriculture area 99.22 ppb during the wet season, and the last polluted station was found at the Station 10 mining area 0.43 ppb during the wet season. Manganese has significant negative correlation with the pH, AC, and sand. On the other hand, it had a moderate correlation with the organic matter and significant positive correlation with the another selected heavy metals. Manganese concentration is higher at the Jamburao catchment, followed by the Chini Han catchment. Manganese concentration at different stations was almost suitable over season, but Station 1 agriculture area showed a significant increase in the wet period. Number 5, barium. Barium concentration varied from 0.74 to 1.25 ppb, an average 4.26 ppb. Maximum concentration at the agriculture Station 3 and during the dry season, and the last polluted was in the forest area during the wet season. Barium had negatively high correlation with the pH, AC, and sand, and had moderated correlation with the chromium, with the significant correlation with the clay and arsenic and manganese and cadmium and zinc. Number 6, lead. The lead concentration ranged between 0.22 to 10.94 ppb, an average of 3.23 plus minus 2.68 ppb. Maximum concentration was recorded at the Station 1 agricultural area during the dry season, and the lowest concentration was found at the Station 10 mining area during the wet season. Lead has negatively correlation with the pH, AC, and sand. However, high positive correlation was found between the lead and another 9 selected heavy metals. Number 7. Zinc. The zinc concentration were varied from 0.10 to 1.92 ppb and averaged 0.3773 plus minus 0.250 ppb. Maximum zinc concentration was correlated at the Station 7 forest area during the dry season, followed by the Station 8 mining area, while the last polluted station was found at the Station 10 mining area during the wet season, followed by the Station 5 forest area. Personal correlation showed significant negative correlation with the pH, AC, and sand. On the other hand, the zinc had positive correlation with the clay, arsenic, chromium, cobalt, chrome, manganese, and cadmium. Number 8. Cadmium. Cadmium may be present in the aquatic environment at a relatively low level in organic complexes such as carbonate, hydroxide, chlorides of sulfate. Personal correlation showed negative with pH, AC, and sand. However, had a strong positive correlation with salt and all selected heavy metals. Number 9. Chromium. Chromium concentration ranged from 0.44 to 6.61 ppb, an average 2.48 plus minus 1.18 ppb. Maximum concentration recorded at the Station 4 agricultural area during dry season, while the last polluted station was found at the agriculture area, Station 1, in the wet season. The correlation showed that chromium had significant negative correlation pH and moderate negative correlation with the AC and sand. On the other hand, significant positive correlation with the clay and 9 selected heavy metals. Number 10. Nickel. Nickel concentration varied between 0.05 and 32.30 ppb, average of 6.78 plus minus 8.37 ppb. The highest concentration value, 0.32, was detected at the agriculture station in the wet period following by Station 4 agriculture area. Meanwhile, the last concentration value, 0.010 ppb, at the Station 3 agriculture area. Personal correlation indicated that nickel had significant negative correlation with pH and AC and sand. However, nickel had moderate positive with the organic matter, while it had significant positive correlated with the clay, arsenic, chrome, cobalt, manganese, cadmium, zinc, barium, and lead.